In section 3 of chapter 1, we're going to look at how do we solve quadratic equations in standard form. This is standard form, y is equal to x squared plus bx plus c. We have a leading coefficient in this case that is 1. It's a little different when we have a leading coefficient that's 2. And we're going to solve by factoring, using special patterns to factor, and using the zero product property to find zeros. These zeros are also solutions. Key vocabulary you need to know are monomial, that's a polynomial with one term. For instance, we might have 3x squared. That's a single term. Even though it has a coefficient and a variable part that's to a power, it's one term. A binomial has two terms, so we might have 3x squared plus x. That's a polynomial with two terms. Or a trinomial, which has three terms. So if I had 3x squared plus x plus 5, that has three terms. Monomial, binomial, trinomial. We want to talk about quadratic equations. So what differentiates a quadratic equation from other equations is the degree of the polynomial. And degree is found by what's the highest power of the variable term. In this case, the variable term is to the second power. That makes it a quadratic equation. When the highest power is the first power, that's a linear equation. If the variable is to the third power, a third degree equation would be a cubic equation, and so on. We want to find the root of an equation. The root of an equation is a zero, which can be put into a factor. And the zero of a function is a value of x that makes the function equal 0, and it's also called a solution. So roots, zeros, solutions, they all are essentially the same thing for different polynomials. We refer to them in different ways when we're using them in different ways. Okay, the type of problem that we might solve by using the skills we're working on here is this problem. At last year's school fair, they had an 18-foot by 15-foot rectangular section of land that they roped off for a dunking booth. And they decided it was too small and they really needed 3 times that amount of area. So now they want to figure out, well, we want to lengthen each dimension by the same number of feet so that we can triple the area, and then we have to get the right amount of rope so that we can put a rope around that area and keep people out. So how do we go about doing that? As we go through, we're going to practice some skills, and as we finish, then we're going to solve this problem. So the first thing we want to work on when we're dealing with a quadratic function with a leading coefficient of 1, then we're able to focus primarily on the final term in the trinomial, which is the constant term. Okay, now you notice this is called the constant term. All of these are constant terms. It's called the constant term because the variable isn't present in this term. So I can keep changing the value of x, but the value of this final term in my trinomial, it will never change. It will remain constant. So it's called the constant term because its value isn't related to what value of x I've selected for x. Whereas this term, as I change x, the value of this term will continually change. So we're going to look at finding all the different possible factors of this constant term because that's our first step in factoring. So 5 is a prime number, so its factors are itself and the number 1. Here we have 40. Different factors are 40 and 1. It could be 20 and 2. It could be 10 and 4. And it could be 5 and 8. Okay, so if you're wondering how I went about that, you notice I started with the number. I divided it in half, so I factored a 2 out of it and I multiplied the other side by 2. I factored a 2 out of it, I multiplied the other side by 2. I factored a 2 out of it and I multiplied the other side by 2, and that helped me find all these factors. Equally, you could do a factor tree. You can do whichever works the best for you. So factors of 56 are 56 and 1. I could have 28 and 2. I could have 14 and 4. And I could have 7 and 8. Okay, so now we've listed up the factors. Let's move on and see how those factors come into play in factoring. Okay, we should already know by now that when we multiply binomials together, we have to follow the distributive property, and what that basically means is it can be simplified by thinking of FOIL. Right? So we multiply the firsts together, then we multiply the outsides together, then the insides together, and then the last terms together, and then we combine like terms. So what you can see is what's critical here is how these two terms, these are the things that combine. Right? When I multiply my outsides on my insides, I create terms that are like terms, and it's how they combine that can create this middle term. So what these factors are determines what this middle term is. So we're going to use the information we already used from factoring the constant and some new information from evaluating the signs in the polynomial to be able to factor these. So the nice thing about a prime number is it only has one set of factors, the number in itself. And when I look at this term, this sign, the second sign in the polynomial tells me a great deal about what's going to happen in the binomial, right? So when I think of this, I know that there are only two possible solutions when I just consider this. I know that this is going to be either -5 and -1, because -5 times -1 equals +5, or it's going to be +5 and +1. So when this sign here is a plus, I know that the signs in my two binomials have to be the same sign, because to get a positive number, I either have to multiply a negative number times a negative number, or a positive number times a positive number. So the signs will be the same. Then I will know which sign they are by looking at this term, right? So this is the correct situation here. And if I multiply them out to check my work, you'll see how that comes into play. So if I multiply this out, x times x is x squared, x times -1 is -x, -5 times x is -5x, and -5 times -1 is +5. So I got the +5, and I got the x squared, but you see my middle term becomes -6x instead of +6x. On the other hand, when I multiply this one out, I'll still get x squared, and this time I'll get +x, and then I'll get +5x, and still get +5. So I have x squared plus 6x plus 5. This is the correct one, so this is my solution. Okay, equally, if this is a minus sign, right? So remember, if this is a plus sign, it means the signs in the binomial are the same sign in each binomial. If this is a minus, then there'll be different signs because I'll have a positive number times a negative number. But we'll have an example like that in a minute. So if we do this again, we want here to look for the factors of 56 that will do this, that will add up to be 15. And following the same rules that I did before, this is a plus. That means that the signs of my binomials will be the same. This is a plus. That means they'll both be pluses. So now I'm going to have r plus and r plus. And now I need to find the factors of 56 that will add up to be 15. So if we go back to where we listed all of our different factors, factors of 56, well, 56 and 1 make 57, 28 and 2 make 30, 14 and 4 make 18, 7 and 8 make 15. Oh, 7 and 8 make 15, so these are the factors that I want. So if I put in 7 and 8, those will add up to be 15. If I want to check my work, I go ahead and multiply it out. R squared plus 8r plus 7r plus 56. And I combine like terms. 8r and 7r is 15r, which we already checked. Yeah, this is that. I did it right. This is my solution. Okay, so we did the negative 40 as well, but this is now a different situation. This is now a minus. Okay, so I want to look at this minus, and I need to figure out what does that mean. Okay, so it means that I have to have a negative number times a positive number to get this minus, so I know I'm going to have different signs in my binomials. One's a plus and one's a minus. I know that the first terms are b because b times b will give me b squared. That's my firsts. Okay. Now I'm going to look at my lasts, my factors of 40. But now I want, because I'm going to have a positive number plus a negative number, those will make a difference. So I want a factors of 40 that have a difference of 3. Let's go back and take a look at those. Here's 40. 40 and 1, those have a difference of 39. 20 and 2, those have a difference of 18. 10 and 4, those have a difference of 6. 5 and 8, okay, yeah, those have a difference of 3. These are the ones I'm going to use. So now I just need to know where do they go. Okay, so I know I'm going to use 5 and 8. But which one goes where? Well, the answer comes back from that first sign. Right? I need to come out with plus 3. That means that the bigger number, 8, is going to have to be positive. So if I put plus 8 and minus 5, that should give me what I want. So when I go ahead and multiply this out, I'll have b times b is b squared. I'll have b times minus 5 is minus 5b. I'll have 8 times b, that's plus 8b. And I'll have 8 times negative 5, that's minus 40. So I know I'm good. I got my first term, I got my last term. And now we'll check to see if these combine to make my middle term. Minus 5 plus 8, that's plus 3b, minus 40. Okay, yeah, this is exactly the same. So that checks out. This is my solution. So for your practice, it's good to take a look and see what would have happened if I'd put them in the wrong place. So what if I had put b plus 5 and b minus 8? So what if I had put them in the wrong place? When I multiply it out, I'll still get b squared. Then I'll get minus 8b and plus 5b and minus 40. So you'll notice, right, no problem with the first term, no problem with the last term. But this middle term becomes b squared minus 3b minus 40 because I have negative 8. All right, so when you're looking at this, the signs give you guidance to what goes where. And then checking your answer allows you to make sure that you actually put them in the right place. So if you take the time to check your answer, you won't make mistakes like getting them in the wrong spot. You'll find it really quick and go, oh, I just put them in the wrong place. I got all the right numbers, but I've got a wrong sign. That means they're in the wrong place. Okay, another thing we want to work on is recognizing and using special patterns. So there are some special patterns like this one, the difference of two squares. The difference of two squares can be factored to be a plus b times a minus b. And in this case, you'll see that a, that's the square root of the first term, and b is the square root of the second term. So if you're trying to identify this pattern, what you want to look at is this a perfect square? Oh yeah, that's x squared. And is this a perfect square? Yeah, it is. It's 6 squared. So once I know that they're perfect squares, then I can take the square roots and I can plug them into this pattern. So x would be a, 6 would be b, and I know this is going to be x plus 6 times x minus 6. All right? And why does this work? You could factor this the same way. I could be looking at factors of 36 that have a difference of 0, because if I wrote this full out in standard form, right, it's x squared plus 0x minus 36. I know that my signs are going to be different, right, because this is a minus. I'll have a plus and a minus. And I want factors of 36 that have a difference of 0, so those would have to be the same number to have the difference of 0. So I'm looking at 36 being a square. I could factor it the same way we just did and still come out with the same answer. Okay, and if I multiply these together to check my work, x times x is x squared, x times minus 6 is minus 6x, 6 times x is plus 6x, and 6 times negative 6 is negative 36. So you see what happens here in the middle, and the reason we have no middle term is because the outsides and the insides are opposites. So this just simplifies to be x squared minus 36. I know I did it right. This is my solution in terms of factoring. Okay, also we want to look at perfect squares. Perfect squares are really important because we're going to use them also in later sections when we start solving by completing the square. When we talk about completing the square, this is the square we're going to be completing. It's the square of a binomial. So I'll start in a completing the square problem. I'll start with part of this perfect square trinomial. I'll put something into it to make it a perfect square trinomial so that I can then factor it to be the square of a binomial, which lets me square root either side of the equation to solve it. So we're learning a lot of different skills to solve. But right now we just want to be able to identify a perfect square trinomial. So you'll notice that in all of these special patterns, the first term is a perfect square, and the last term is a perfect square. And then we're checking these middles, right? Here I need a middle that comes up to be 0. And here I need a middle that will be 2 times the square root of the first term times the square root of the last term. So let's find those square roots. T squared, the square root of t squared is t. The square root of 64 is 8. Right? So this is a perfect square. That's a perfect square. And I want to check this middle term to see, is it 2 times t times 8? Well, yeah, 2 times t times 8 is 16t. And now I can make a binomial, a perfect square of a binomial. You notice also in the signs give us clues, right? These have to be pluses. And then these signs tell us the sign in the binomial. Right? If this first sign is a plus, there's a plus in the binomial. If the first sign is a minus, there's a minus in the binomial. So once I've identified this, I know that this is going to be t, this comes from here, minus, that comes from there, 8 squared. Okay, so the first term in my binomial is the square root of the first term in my trinomial. The sign in my binomial is the first sign from my trinomial. And the last term in my binomial is the square root of the last term in my trinomial. And this makes a perfect square. But remember, I can only do that if this middle matches up to this pattern of 2 times a times b. Okay, let's do another one of those. So here I'm looking, is this guy a perfect square? Yeah, n squared is the quantity n squared. 49, that's 7 squared. So now we check the middle term. Is this 2 times n times 7? 2 times n times 7 is 14n. Yeah, that works. So now I'm going to pull this term, the n. I'm going to pull this sign, the plus, and I'm going to pull this number, the 7, squared. That's my binomial squared. Again, if I want to check it, n plus 7 times n plus 7, I can always check these things. N times n is n squared. N times 7 is 7n. 7 times n is also 7n. And then 7 times 7 is 49. If I combine like terms, n squared plus 14n plus 49, does that match my original equation? Yes, it does. So this is correct. Okay, now we want to talk about the zero product property. So what we've done so far is we've identified factors of the constant. We've used and tested factors of the constant so that we can make the correct middle term and correctly factor quadratic functions. And now what we want to do is we want to use this new concept, the zero product property, so that we can find solutions of our quadratic functions. And that was one of our other learning objectives for this section. And the zero product property is a pretty simple idea. It basically says that if I have two things that I'm multiplying together and the result is zero, if the product of two items is zero, then one of those two items had to equal zero because it had to be 0 times something to equal zero. If they're both not equal to zero, then it would never equal zero. Okay? And what that means for me in factoring is I'm taking this trinomial and I'm going to make it two binomials that are being multiplied together. If it equals zero, then one of those two binomials must equal zero. And this is how we solve. So now I want the factors of 12 that will add up to 8. Well, let's see. 12 and 1 add up to be 12. Then I could have 6 and 2. Okay, those add up to be 8. There we go. I know that my signs are the same. And I know that they're both minuses. So I'm going to have x minus, x minus. When they're the same, it doesn't matter where I put them. Right? And now I factored this. So what this says is that this quantity, x minus 6, times this quantity, x minus 2, equals 0. If it equals 0, then either x minus 6 equals 0 or x minus 2 equals 0. So if I take each of them and I set them to be equal to 0, and I solve them, in this case x is equal to 6, in this case x is equal to 2, I will find the two solutions to my quadratic function. Equally, we might call these roots. If I take a root and I plug it into this binomial, x minus a root, right? We call roots k values in this particular case with polynomials. I can take a root, 6, plug it into a binomial, x minus 6, and this then is a factor of this function. So we're going to use these as we progress through this. We can take a polynomial function, factor it, find solutions, or we can be supplied solutions, put them into factors, multiply them together, and create the original equation. So either we can take equations and find solutions, or we can take solutions, known solutions, and figure out what was the equation that made this. Okay, here's another one. This is, again, a special pattern. This is the difference of two squares. You can see that a squared is the quantity a squared, and 49 squared, or 49, sorry, is 7 squared. I know it fits that pattern of the difference of two squares, so I could say this is a plus 7 times a minus 7. If I didn't catch that, I might say, oh, well, I want factors of 49 that have a difference of 0. And that would be 7 and 7, right? I know that if I have this equation, 0a minus 49, I know that I want factors of 49 that have a difference of 0. I know that binomials have different signs because this is a minus. And so 1 and 49, that doesn't have a difference of 0. 7 and 7, that does have a difference of 0. So if I don't catch the fact that it's the difference of two squares, and I continue to engage with the problem with other skills that I already have, I can still factor it and get the right answers. Okay, so in this case, if these two binomials multiplied together equals 0, that means that either a plus 7 equals 0 or a minus 7 equals 0. So a could be equal to negative 7 or a could be equal to 7. These types of binomials also have a name. When you have binomials that are identical, except for just changing the sign, they're called conjugates. And conjugates create the difference of two squares, which is something we're going to do in later chapters. So try to remember in the back of your head that, oh yeah. Binomials that are the same but have different signs, they're called conjugates. And what's great about them is they give me no middle term, which means that if I'm looking to solve, I don't have the problem of having a variable squared and a variable to the first power. And when I'm doing other things that I need to accomplish, that's sort of the same as well. All right, now at times you'll have a binomial like this where you see that I have the variable in each of the terms. So this leads us to an important concept in factoring, which is the first thing you really want to do with any polynomial that you want to factor is you want to look to see, is there something that I could factor out of all the terms? So you see I have n squared here and I have n there. So it means I could factor an n out of the binomial to create a monomial and another binomial. Now if this equals 6, if n times n minus 6 equals 0, then again the zero product property says that either this equals 0 or that equals 0. So to find my solutions, n equals 0, and n minus 6 equals 0, so in that case n would be equal to 6. So n can be equal to 6 or n can be equal to 0. Okay, returning on to the problem we started with. I know that if I want to calculate the area here, it would be 18 times 15, which would be equal to 270 square units, whatever the units are. Let's say they're feet. Okay, so let's go ahead and say that we're talking about feet. So if the original area was 270 square feet, and my new area is going to be 3 times that, I could say that 3 times the original area needs to be equal to the new area, which is going to be the unknown distance x that we're making things larger by, plus 15 and plus 18. So when I multiply these guys out, this is going to be 810, and this becomes x squared plus 15x plus 18x plus 270. And when I combine like terms, right, we're going to make this equal 0. So I'm going to subtract 810 from either side, and I'm going to combine like terms. I get x squared plus 33x minus 540. So now, if I look at this, I'm going to look for the factors of 540 that will have a difference of 33. And I'm going to go ahead and start working on the factorization of this. I know that I'm going to have x in each binomial because my first, x times x makes x squared. I know that the signs are going to be different because I need to have a positive number times a negative number in order to get a negative result. And now I'm going to look for the factors of 540 that will have a difference of 33, and I know that I need to make the bigger one positive. Okay, that will allow me then to end up with a plus 33. So when you look at the factors of 540, right, we have 540 and 1. Those don't have a difference of 33. I have 270 and 2. Those don't have a difference of 3. I have 135 and 4. Those don't have a difference of 3. I have, I'm going to go ahead and take a 5 out of these guys. So I'm going to have actually a 3 out of it, 45 and 12. And now you see that these do have a difference of 3. So if you're looking at how I'm working, I took the 540, and that was times 1. I divided it in 2. I took a 2 as a factor out of here, and I moved it to the other side. I took a 2 as a factor out of here again, and I moved it to the other side. And then I took a 3 as a factor out of there and moved it to the other side. So I'm just dividing this number by a number, and whatever I divide it by, I multiply the other side by it. So I still have the same factors. Equally, you could do a factor tree. I just think this sometimes is a little faster. So I know that 45 and 12 have a difference of 33. This will be plus 45 and minus 12. So when I look at this, I think of what are my solutions for x. So x could equal, well, actually let's really just set our binomials to be equal to 0. It's easy to sort of start shortcutting. If x plus 45 is equal to 0, then x is equal to negative 45. And if x minus 12 is equal to 0, then x would be equal to 12. So now, and this is something I mentioned in another lecture, that it's very important as you work on word problems that once you've found solutions, so I found 2 solutions and I need to pick one. Okay, so now we want to answer the question, what length of rope do I need to enclose the new section? So first I have to find out what the perimeter is, and then I have to calculate the perimeter of the rope to go around this perimeter. So I have 2 more steps still to go, and the first thing I have to do is I have 2 solutions. I have to decide which one is correct. And it's important then that when we think of distance, right, if I use negative 45 and I add it to 15, 15 plus negative 45, that's going to make a distance of negative 30. Can I have a negative distance? I really can't, right? So I'm going to go ahead and use the 12, right? So x plus 12, or sorry, 15 plus 12 is this distance, and 18 plus 12 is this distance, so this distance is 30, and this distance is 27. So if we're talking about how much rope we need to go around, I'll have 2 times 30. Sorry, I'm going to extend my page again. I have 2 sides that are 30, and I have 2 sides that are 27. So this is 60 plus 54. That's going to be 114 feet. That's the amount of rope I need to go around this area, which is 3 times the size of that area. So by using some of the skills that we found, we created a construct of 3 times this area equals that area. We introduced our unknown. We created a quadratic function. We combined like terms, and then we factored, found solutions, tested them for validity, and selected one. Now, it isn't always that you're going to select one. In this case, negative distance is not something that occurs in the world. Okay, so we've selected the positive distance, calculated our perimeter, and answered our question.